Okay guys, this is the first video in a long series of videos that will cover Chem 120, College Chemistry 1. I'll be presenting my lecture notes, which covers the OpenStax chemistry textbook. Here is the chapter opener for Chapter 1, which is entitled Essential Ideas. The idea of this chapter is to present, to give an overview of chemistry. That's this chemistry in context section where they'll highlight different applications of chemistry in the world around us. These other sections here will cover two more sections in this video, phases and classification of matter, as well as the physical and chemical properties. And we'll save these other topics for a later video. So here is the section opener for chemistry in context. There's a lot of narrative in the chapter which outlines the history of chemistry to some extent and provides lots of examples in everyday life. I'm going to be skipping most of that here in the video, and I'm going to focus on these two important points here which connect with the general education objectives of the course. And so I need to say a little bit about the scientific method and about hypotheses, theories, and laws, and so forth. And then we will quickly move on to the other sections. So I have just a couple slides here. Why study chemistry? So beyond the default answer, because I have to, the reason it's useful to study chemistry is that just about everything that you do or encounter in life involves chemistry in some way, whether it's consciously or unconsciously. Chemistry is somehow involved in what you encounter in everyday life. Another reason why it's useful is chemistry provides us with the tools that we need to control both matter and energy, and that's a powerful thing if you can do that. In chemistry, we like to think about the composition and structure of matter and how those relate to the properties of matter that we observe in nature. And then it also allows us to create changes in matter, which is very powerful. And so in order to apply chemistry, you need to have chemical knowledge and problem-solving skills, and that's what we develop right here in Chem 120. So that's the focus of the course, is acquiring chemical knowledge and developing our chemistry problem-solving skills. Chemistry is often called the central science, and that's because it is useful to just about every other field in science. And so this diagram here shows a network with chemistry in the middle, and then you can see all of these other disciplines that make use of chemistry. So you may be interested in medicine or biology or perhaps agriculture, biochemistry, of course environmental science is important in today's world. Or you may be interested in engineering applications and things like that. The point is here that the basic concepts in chemistry are useful to all of these different disciplines, and so that's probably why you're in this class. Like all sciences, chemistry uses the scientific method, and I know that you've seen this in probably every science class you've ever had, but if you'll just humor me for a minute. As you know, the scientific method starts with observation, and I like this part here. It also starts with curiosity. So if you're curious about something and you observe it, then you want to make a connection between what you're observing and what causes it. And so from there you would make a hypothesis, which is an educated guess. And then the next step is to test that hypothesis using an experiment of some sort. And the simpler your hypothesis is, the easier it is to test. And so we'd like to have simple hypotheses that can be tested very easily and give us a very objective answer. That's not always possible, especially when the system that you're interested in is very complicated. But in any case, what you do is you go from making guesses to experiments, acquiring more knowledge, then you improve your guesses and do more experiments and so on until you get some results that are consistent with what your hypothesis predicts. And if you're a professional scientist, you would probably write that result up in a paper, submit it to a journal, hopefully it'll get accepted, and that will contribute to the body of knowledge in that discipline. Other people will then take that knowledge, they will use it in their own applications, or they'll just test it outright. And if they find that your experiments don't hold up, then it gets kicked back to the hypothesis stage. Otherwise, if the knowledge that you've created with your experiments is well supported, you might be lucky enough to have your observations become a scientific law. Or if you have a more elaborate set of ideas, those might wind up in some theory of nature. What I like about science is this point right here, that it is a self-correcting cycle. So the way this whole procedure works here is that the explanations of what we observe are supposed to get better and better through this constant testing and doing new experiments and so forth. And so science is a self-correcting cycle. It's supposed to get better with time. Well, that's enough of that. We'll move on to the next section of the chapter, which involves the phases of matter and classifying matter. And so what I've highlighted here are the important learning objectives. I probably could have left off this one here, distinguishing between mass and weight. I'm not going to focus on that at all. But we need to know the basic phases of matter, which you probably already know, solid, liquid, and gas. And then we need to know how to classify matter. Okay, that's the most important part here. And then we'll also do this part here. We'll use our first law in chemistry, the law of conservation of matter, and I think that's what we're going to start with, actually. No, we'll start with the phases. So, phases of matter. Matter is often classified by its physical state, which we call the phase of matter. There are three phases of matter: the solid phase, the liquid phase, and the gaseous phase, and we use in parentheses S, L, and G to denote those different phases. Solids, as you know, are rigid. Okay, so they're a rigid form of matter. They have a fixed volume and a fixed shape, right? They don't fall apart. Liquids, on the other hand, and gases are not rigid forms of matter. They are fluid forms of matter. Okay, so they flow. They change their shape. Liquids are called incompressible fluids because they have a fixed volume. Gases, on the other hand, are compressible fluids because you can squeeze a gas into whatever container that you want. So a gas will fill any container that it's occupying. Okay, now we'll look at the law of conservation of matter. So this is our first scientific law that we'll use in chemistry, and it states that the amount of matter, or mass, remains a constant during a physical or chemical reaction. That is to say, matter is neither created nor destroyed. So, a definition, mass, and I'm using the symbol lowercase m to denote mass. Mass is a quantity of matter, so it represents the amount of stuff in whatever material object you're talking about. The larger the mass, the more matter you have. A physical reaction is one in which the physical state of the matter is changed. For example, a phase transition. So suppose you had ice and it melts to water. We would call that a physical change or a physical reaction. Contrast that with a chemical reaction where the identity of the matter actually changes. So you go from one type of matter to a totally different type of matter. Not just a phase change, but a complete change in the composition and structure of the matter. And we will be using chemical equations. Here I have one written in word form, where you start with some reactants, they react to yield whatever products you have at the end of the chemical reaction. So we'll talk more about chemical reactions in a lot of detail later. For right now, we want to focus on how to apply this law of conservation of matter to chemical reactions and physical reactions. So the law of conservation of matter and mass tells us that the mass of whatever you have before the reaction takes place must equal the mass of whatever you have after the reaction takes place. And so it's no more difficult than that. That's the whole thing right there. Here I'm making it a little bit more complicated by pointing out that not necessarily all of your reactants will react. So you can take this mass of what you have before the reaction and you can divide it into two parts. The part of the reactants that are actually consumed in the reaction, plus whatever reactants you will have left over that don't react. That's what I'm calling the excess reactants. Likewise, this mass after the reaction would be then a sum of two terms, the mass of the products that are formed, so the new products that are made, plus whatever extra reactants did not react. And you'll notice that this term is on both sides of the reaction, and so you could cancel it out, and you're left with just the mass of the reactants that were consumed equals the mass of the products that were formed. Let's look at an example. Okay, so here we have an example problem. It says that you heat 2.53 grams of metallic mercury in air, which produces 2.73 grams of some red-orange residue called mercury oxide. Assume that the chemical change is the reaction of the metal, that's the mercury, with the oxygen in the air, and they want us to calculate what is the mass of the oxygen that reacts. Well, let me work that out over here for you. Okay, so we have a reaction that's going on, and so I'm just going to write it in words. You have mercury plus oxygen is giving us this residue. Okay, so that's the chemical reaction that's taking place. The law of conservation of mass, or matter, allows us to take this chemical equation and then to write it as an equation involving masses. So you could write the mass of the mercury plus the mass of the oxygen that reacts must equal the mass of the residue. Okay, so you can take the chemical equation and convert it into a mathematical equation involving the masses. So you'll notice that they give us the mass of the mercury and the mass of the residue, and they ask us to find the mass of the oxygen. So we will rearrange the equation, solving for the unknown. Like that. And then we can substitute in the numbers. So 2.73 grams of the red-orange residue minus the 2.53 grams of the mercury. And so we'll be left with 0.20 grams for the oxygen. Okay, so that's the law of conservation of mass. The mass of what you have before the reaction needs to equal the mass of what you have after the reaction. And so we've used the law of conservation of mass to solve this little problem. In the follow-up question, let's suppose you take that residue. So now we're starting with the residue that we had, and we strongly heat it up, and we find that it decomposes back into mercury and releases oxygen. So if we take this 2.73 grams of residue, heat it up, what mass of oxygen do we expect to get back? Well, it's just a trick question. It's the same 0.2 grams that we calculated in point A. Here, the next slide is another example problem, one that I'm going to leave it to you to work out on your own. So solve this one as an exercise for yourself, and we'll get right back to the rest of the presentation. So we'll move on to the next topic, classifying matter. Matter is typically classified by its composition, and there are two broad categories of in which you can classify matter. Matter can either be a pure substance, or it can be a mixture. So these are the two broad classifications of matter. A pure substance is one that cannot be decomposed by physical reactions, meaning you can't melt the substance or you can't separate a pure substance from itself because it's just one thing. It has constant composition and it has unique and uniform properties. There are two types of pure substances. Okay, so under the category of pure substances, we have elements and compounds. Elements are substances that cannot be decomposed by chemical reactions. For example, you may have heard the old lore from alchemy where the old alchemists tried to take lead and convert it into gold. This is not possible to do because both lead and gold are elements, so there's nothing you can do to lead to turn it into gold. Compounds, on the other hand, are composed of different elements and they can be decomposed by chemical reactions. So it is possible to take a compound and perform a chemical reaction that will convert it into its elements, at least in principle. The other broad category of matter, mixtures, these are substances that can be separated by physical reactions. And so they have variable composition, which means that you can make up mixtures with different amounts of the components. So think of something like salt water, something easy like that. You could have a solution that has a lot of salt dissolved in it, or you could have a solution that has only a little bit of salt dissolved in it. That's what I mean by a variable composition. Okay? You can alter how you mix these substances together. Within the category of mixtures, there are two types. There are homogeneous mixtures, which are also called solutions. These are substances that have a uniform composition and properties. And the way to think about that is that the components that are mixed together in a solution are mixed at the molecular level. And so you can't distinguish different parts of the mixture from one another because they're combined at the molecular level. Whereas a heterogeneous mixture is one that has a non-uniform composition, and you can distinguish different parts of the heterogeneous mixture. So think of something like a mixture of sugar and sand, right? If you mix sugar and sand together, you can distinguish the sugar crystals from the sand. And so you can just look at the mixture and say, oh, that part's sugar, that part's sand, etc. So that's what I mean by heterogeneous. You can distinguish the different components of the solution, or of the mixture. These here are graphical examples of what we've been talking about. Up here in the upper left, this red-orange compound, this is what we had from the example. So this would be a mercury oxide. It's a compound. If you heat it up, you can decompose it into liquid mercury metal, and then oxygen gas. Okay, so a compound can be decomposed into elements. On the bottom set here, we have a heterogeneous mixture of oil and water, and there's probably some food coloring added to the water. And you can distinguish the oil part of the mixture from the water part of the mixture. They're not the same. You can tell that there's a boundary between them, and you can distinguish the two parts. Contrast that with a sugar solution here, this energy drink. The sugar is dissolved in the water, and the food colorings are dissolved at the molecular level. And so you can't distinguish where the sugar is from where the water solution is, or from where the water is. It's uniform. And so that's what makes a solution, is that the components are mixed at the molecular level. And so this flow chart here illustrates all of the different terms that you need to know. Okay, so you need to know that matter can be a pure substance or it can be mixtures. And then you need to know that pure substances are either elements or compounds. These are related to one another chemically. That is, you can decompose compounds chemically to give you elements. You can take elements and recombine them chemically to give you compounds. Mixtures, on the other hand, we classify as being heterogeneous or homogeneous. Homogeneous or uniform. Heterogeneous mixtures are not uniform. Okay. This last section here, I have just one slide on it. We want to be able to distinguish physical and chemical properties from one another. A physical property is a characteristic of matter that is not associated with a chemical, with the chemical composition. So, for example, the boiling point of a liquid, or its melting point, or its density, how much it conducts electricity, etc. These are all properties of matter that are not associated with a change in the chemical composition. And so these are considered to be physical properties of matter. A physical change is one that involves a change in the state of matter, for example, melting or boiling, but it doesn't involve a change in the chemical identity. So, for example, if you take water and you boil it to give you water vapor, you're still dealing with water, it's just in a different physical phase. Here on the left, we've got some candle wax that's being melted, and so the part of the wax that is simply melted into the liquid phase, that's still candle wax, it's just in a different phase. However, at the point of the flame where the candle wax is actually being burned, there you have a chemical change that's going on. And so chemical properties are associated with a change in the actual composition of matter, how flammable something is, whether or not it's toxic, is it acidic or not, how much energy does it produce when you burn it. These are properties that involve chemical changes, changes in the actual identity of matter. And so they involve chemical reactions. So for example, when iron rusts, the fact that iron reacts with oxygen to form rust, that's a chemical property of both iron and oxygen. Different fuels, the fact that they burn in combustion reactions, that's a chemical property of those substances. And there's other chemical reactions that are illustrated here. So here you're cooking food. That actually changes the identity of the different compounds within the food. When fruit ripens, chemical reactions are occurring, etc. So we're going to go ahead and stop this video right here, and we'll pick up with measurements next time.